This is lesson 5.2, inner product spaces. Now, before I even get into anything with this lesson, let me just start by saying this. Don't make an inner product space anything more than it is. It's not really a complicated idea at all. Very, very simply, an inner product space is a vector space. We've talked a lot about vector spaces before. We've done a lot of work in vector spaces. That's all it is, with the exception that it has to hold certain characteristics and hold under certain conditions. So not every vector space is necessarily an inner product space, but that's what we're going to talk about. So an inner product space, as we said, is a vector space. And specifically then, it's a vector space that has what's called an inner product. And if you look at the definition here, it says let U, V, and W be vectors in a vector space V, and C be any scalar. An inner product on V is a function that associates a real number uv with each pair of vectors u and v that satisfies the axioms listed below. And we've got 4 axioms obviously listed here. So let me just kind of paraphrase what this is saying. So an inner product space has an inner product. An inner product is simply an operation that we would perform on vectors within that vector space. And as long as performing that operation on those vectors maintains these 4 axioms, then it's an inner product. Okay, so there are different inner product spaces. There are different inner products. What we're going to do is start by focusing on one that we're already familiar with, and that is the dot product that we learned in the last lesson. So dot product, remember, is where we basically take 2 vectors and we multiply their components and add them together and get this scalar. By the way, an inner product will always give you a scalar. Okay, so that's another thing that may help in remembering what that inner product is or a characteristic of it. So, for example, we're going to show that the dot product is an inner product on any n space in R. Okay, so again, that just simply means that these 4 axioms in this definition have to hold true. So let's kind of put this into context before we even go through the kind of the proof, so to speak. Let's take u dot v, and I'm going to put this up here. Let's take u dot v, and let's just think about what each dot product would look like for each of these 4 axioms. So basically, the first axiom says that you can perform the operation on the 2 vectors in either order. In other words, for a dot product, then this is saying that I could take u dot v, or I could take v dot u, and I would get the same answer. The second one says if we introduce this third vector w and we add it to v before taking the dot product, we would get the same answer as if we took the dot product of uv and added the dot product of uw. Okay, so again, just kind of in notation of what this would look like, if I take u times the dot product of v plus w, that would be the same as if I took the dot product of uv plus the dot product of uw. Number 3 says that I can take a scalar and multiply it by the dot product. So I'd find the dot product first and then multiply it by the scalar. Or I should be able to multiply vector u by the scalar and then take the dot product. So this would just simply be c times u dot v, or c times u and then and then times the dot product of v. All right, number 4, the last one, says that if I take the same scalar, or the same vector and perform the operation on itself, it's always going to be greater than or equal to 0. And if I perform that operation on the same vector on itself, it'll equal 0 if and only if the vector is the 0 vector. Okay. Notice again that the inner product is a scalar, so this is actually just 0, the number 0, and this would be the vector, the 0 vector with all zeros in its components. Okay. So what this says then really is that if I take the dot product of a vector with itself, that's always going to be greater than or equal to 0. And then the second part basically says that if I take the dot product of the vector in itself, that it's going to equal 0 if and only if v is the 0 vector. Okay, so let's go ahead and we're going to run through each of these 4 just to show that the dot product is an inner product for any n space. So let's let u just be the components u1, u2, u3, and so on. Let's let v be the components v1, v2, v3, and so on. So if I take the dot product then of u and v, that's going to give me u1 times v1 plus u2 times v2 and all the way up to un times vn. Now, we know that multiplication can be done in either order, so I can flip this around and say v1 times u1 plus v2 times u2 all the way up to vn times un, which is the dot product of vu, so v dot u. Okay, so order doesn't matter when we're doing dot product. We can put that in either order. So 1 holds. Number 2 says that we can add this vector to v, or we can take the dot product separately and then add them together. So starting with the left side, this is basically saying that if I take u times the dot product of v plus w, I'm going to have u1 times the quantity v1 plus w1, and then plus u2 times the quantity v2 plus w2, and again all the way up to un times vn plus wn. All right, well, if we distribute through and simplify this, we have u1 v1 plus u1 w1 plus u2 v2 plus u2 w2 all the way up to un vn plus un wn. Well, if you notice, then basically what we have is u1 v1, u2 v2, all the way up to un vn. That is the dot product of u and v. And then u1 w1, u2 w2, un wn is the dot product of u and w. So number 2 holds. Number 3 says that I can take a scalar and multiply it by the dot product. So if I take the scalar and multiply it by the dot product of u and v, well, that's going to give me c times u1 v1 plus c times u2 v2 plus up to c times un vn. Well, again, we know that we can move things around with multiplication. We can regroup things. So I'm going to regroup this c u1 times v1, c u2 times v2, and then up to c un times vn, which is basically c times, it's the other half of this, right? Now I'm multiplying u times c. I'm over here on the right side. I'm multiplying u times c and then taking the dot product with v. I'm multiplying c times u first, and then I'm doing the dot product, multiplying those 2 quantities together. So this is the dot product of cu with v. So number 3 holds. And then finally number 4 says that if I take the same vector times, or take the dot product of the same vector with itself, it's always going to be greater than 0. So let's take the dot product of v and v. That's going to give me v1 times v1 plus v2 times v2 up to vn times vn. Well, v1 times v1 is just v1 squared. v2 times itself is v2 squared up to vn squared. And obviously when we square a number, it always comes out positive. So in this case, the smallest any of these single terms could be a 0. Therefore, this has to be greater than or equal to 0. And then for the other part of it, the only way to get 0 is if the vector itself is the 0 vector. Well, again, thinking about adding all these terms together, the only way I'm going to get a value of 0 is if each of those individual values is 0, which means v1 has to be 0, which means v2 has to be 0, vn has to be 0, and therefore it would have to be the 0 vector also. So 4 holds as well. So all four conditions hold, all four axioms hold, so the dot product is an inner product for any n space in R. Okay. Now, I did that partly to just kind of show you that proof and show that the dot product is that, but also just so you can really see and understand how each of these four axioms play out. And this is really all we're doing is we're taking an operation, we're applying that operation to vectors within the vector space, and as long as those four axioms hold, it's an inner product for that inner product space. All right. Okay, so let's move on then, and let's do another example here. And we're going to show a different one now, a little bit different. We're going to show that uv equals u1v1 minus 2u2v2 plus u3v3 is not an inner product on R3. So this is the operation. This is how we're defining the operation. So all we need to do is simply show that there is a vector in R3, or vectors in R3, depending on which axiom we want to show isn't true, and basically do exactly that. We need to find an axiom in this list that wouldn't hold true for one or more vectors in R3. So I'm going to focus on number 4, and specifically this first part that says if I take a vector and apply the operation on this with the same vector twice, that it has to be greater than or equal to 0. I'm going to try to show an example where it's not greater than or equal to 0. So for example, let's let v equal, how about 2, 3, 1? That should work. So in this case, u1 is actually also v1, right? So because we're using the same vector it's on itself, it's really v1, v1, v2, v2, v3, v3. So in this case then, applying this operation is going to yield 2 times 2 minus 2 times 3 times 3 plus 1 times 1, which is 4 minus 18 is negative 14, plus 1 is negative 13, which clearly is not greater than or equal to 0. And so axiom 4 in that list is not satisfied. And because that's not satisfied, that tells us that this is not an inner product on R3. All right, well, let's move on then to a little bit of a different topic here. Let's talk about length, distance, and angle. A lot of the things that we're talking about in this section, even though we're applying it in this thing called an inner product space or using inner products, the mathematics that we actually do is the same as what we've been doing. So don't let kind of that theory cloud the fact that what we're doing here is what we've always done. We're not changing anything mathematically. Okay, so this says that u and v are vectors in the inner space V. The length or norm of u is the magnitude of u given by the square root of the inner product of u and u. The distance between u and v is given by the magnitude of u minus v, and the angle between two non-zero vectors u and v can be found using this formula. So all of this, again, should look very, very familiar. We're just saying, look, what we did before in finding length and angles and all of those things still hold true here in the inner space. All right, so let's go ahead then, and I guess let me make a couple of comments here. First of all, there's a couple things I should probably point out. First of all, as we've talked about before, since we're talking about length, if the length of that vector is 1, recall that is the unit vector. So we'd say then that u is a unit vector, a vector with length 1. Oops, unit vector. Also, just the idea then that if you wanted to find a unit vector, if you had a vector and you wanted to scale it down or up as it may be, we just simply take a vector and divide it by its magnitude, and that would give us the unit vector in the direction of v. So this is a unit vector. It's a unit vector in the direction of v. So just a couple of just side notes. related to things that we talked about before in this same context. All right, let's go ahead and take a look at an example here. It says we're going to find a number of things here for the given inner product defined in R3. So we've got our two vectors. We've got u as 1, 1, 1, v is 2, 5, 2. And here they define what the inner product is. Looks very, very similar to what we actually just did above before. So in this case, what we're going to do is we're going to find uv, which is just to apply this operation. So u is 1, 1, 1, v is 2, 5, 2. So we're going to take 1 times 2 plus 1 times, or excuse me, there's a 2 in front there. So 2 times 1 times 5, and then plus 1 times 2. And that's going to be 2 plus 10 plus 2 is 14. Remember that an inner product always gives us a scalar. So 14 is a scalar, so that would make sense for an answer. B is to find the magnitude of u. So we're going to find the magnitude just like we always have. In this case, for u, it's 1 squared plus 1 squared plus 1 squared. And then taking the square root of that is the square root of 3. And then C is finding the magnitude of V, so same idea. We've got 2 squared plus 5 squared plus 2 squared. Taking the square root of that gives us the square root of 25, and 8 is 33. And then finally D, find the distance from U to V. So remember, this is the magnitude of U minus V, which in this case is going to be the magnitude of, taking u minus v is going to be -1, -4, -1. So then we've got -1 squared plus -4 squared plus -1 squared is 16, 17, 18. So the square root of 18 for that distance between the two vectors. So again, mathematically, nothing changes, same ideas as before. All right. We talked about orthogonal back in the first lesson of this chapter. We remember that orthogonal just simply means that two things are perpendicular to each other. And so in this example now, and in this part of the lesson, we're going to talk about what's called orthogonal projection. So it says let u and v be vectors in an inner product space V such that v is not the zero vector. Then the orthogonal projection of u onto v is given by this following formula. Okay, let me just kind of explain what this is doing. So basically what this is saying is we've got a vector u, and we've got another vector v. Now, v does not have to be horizontal. It's just going to be easier to draw and kind of show what's going on here. Basically what happens then is if I want to find the orthogonal projection of u onto v, what I am doing is I'm taking this vector u, and imagine almost like casting a shadow onto v. But when I cast that shadow, I'm going to cast it in such a way that it goes perpendicular to v. That's kind of the orthogonal part of this. So what I'm finding then is I'm finding this vector right here. All right. This is the projection of u onto v. Now, a couple of things about this. This projection is simply then a scalar multiple of v. Now, in this case, I'm showing that the projection is actually smaller than v, so it would be a smaller scalar of v. It could happen, though, if I extended u way out, like if I extended u way out here, its projection would be out here. Now, obviously, then I just have to do a dotted line, but in this case, then the projection would be longer than v. Vectors obviously have a very particular length. They're not raised, they don't go forever. So it doesn't matter if your projection is within or outside of the vector that you're projecting onto. It is simply a scalar. So I'm going to say this, that the projection is just some scalar a times the magnitude of v. If a is positive, if a is greater than 0, then your projection is going to be in the direction of v, as we see in this example. So here, v is to the right, my projection is also to the right in that same direction. Now, the other situation that could happen here is if I have something like this. I'm going to draw V in the same orientation, but maybe U is coming back like this. So in this case, when I project U onto V, again, U has to be kind of almost like burned into, or kind of this image created into V in a perpendicular direction to V. So I have to extend V backward, and this is actually the projection here. So the vector in this case is going to be right here. This is the vector. This is the projection of U onto V. Again, same idea. It's still just a scalar times the magnitude of V, but in this case, because it's now in the opposite direction of V, that tells me that A is negative, that A is less than 0. This means that my projection is in the opposite direction of V. So opposite direction of V. So that's what we mean by a projection. A projection is simply taking a vector and projecting it onto another vector in a perpendicular fashion. And this is the formula that we're going to use to find the vector. So again, we have inner products, this inner product of U and V on the top and V on the bottom, and then V is just a vector. So we're going to just simply have a scalar, because this is a scalar, this is a scalar, this is a scalar. So that whole fraction is just a scalar, and then we're going to multiply the vector V by that scalar. And that's going to give us this projection, this vector that is a projection. So how exactly does this look? We're going to use the Euclidean inner product in R2 to find the orthogonal projection of U, 2, -2, onto V, 3, 1. Okay, let me start by actually just drawing this. We're gonna graph this and just kind of see what this generally looks like, give an idea of what we might be looking for in our answer here. So we've got a vector 2, -2. So I've got a vector. I'm going to start that at the origin, just down to 2, -2. So this is U. And then V is 3, 1. So here's V. And so in this case, if I project U onto V, remember I have to kind of come back to V in a perpendicular direction to V. So I'm going to come back perpendicular to V. So this is a right angle. So the vector that we're looking for is this vector right here. So even just graphically, it looks like it's about 1, maybe a little bit larger than 1, and somewhere around maybe like 0.5. So again, when we find our answer, we get our answer, that should be our check to kind of say, yeah, we're in the ballpark, or while we're way off, we didn't do something right there. So let's go ahead and do that. Let's find the projection of U onto V. So again, in this case then, we're going to be using the dot product. We're going to take the dot product of UV divided by the dot product of VV, and we're going to multiply that by vector V. That is a V. Okay, so in this case then, the dot product of UV is 2 times 3 plus -2 times 1, and then divided by the dot product of V on with itself is 3 times 3, and then plus 1 times 1. And this whole thing gets multiplied by vector V, which is 3, 1. So our fraction, we've got 6 minus 2 is 4 in the numerator. We've got 3 plus 1, or 10 in the denominator. And 4/10 is just 2/5. I'm going to reduce that right now. This is just 2/5. So multiplying the vector by 2/5 is going to give us 6/5 and 2/5 for our projected vector. So again, if we go back to our picture, we said that the x-coordinate had to be a little bit larger than 1, 6/5, 1.2, and the y value was roughly 0.5, 2/5 is 0.4, and so that certainly makes sense for an answer. So what that says then is that projection is this vector right here. This is the projection of U onto V. All right, let's do one more example and wrap up this lesson. So this is the same thing. We're just going to extend this into the 3 space now, but same exact process. So on this one then, for example, and I'm going to go right into the math on this one. Let's just find the projection right away. And so we're going to take, again, the dot product of UV divided by the dot product of VV, and we're going to multiply by vector U, or excuse me, vector V. So dot product of U and V is 6 times 1 plus 2 times 2 plus 4 times 0. In the denominator, using V dot V, we have 1 times 1 plus 2 times 2 plus 0 times 0. And we're multiplying that scalar by vector V, 1, 2, 0. Okay, so we have in the numerator 6 plus 4 is 10. In the denominator, we have 1 and 4 is 5. Multiplying by 1, 2, 0. So obviously that scalar is just 2, so we're just doubling our vector, 2, 4, 0. Okay, so I'm not going to try to draw this in 3 dimensions, but you can see obviously that what we did in this case is when we projected U onto V, we simply doubled the length of V. So if we were to kind of look at kind of this as a cross section, so I'm not, again, this is not in 3 dimensions, but we're going to kind of just think of what this looks like. In this case then, this is V, this is U, and in doing that projection, right, we basically created a length that was twice the length of V. So this would be my projection. So here's my projection. It's this whole length, which is, in this case, twice the length of V. So this just happens to be 2 times V. Okay. All right, so a few ideas in there, but obviously, just go back, watch the video again, watch some of the examples again if you need to see those again. The book has some examples also that I certainly didn't go through. Otherwise, if you've got any questions, reach out, let me know, and I'll see you in the next lesson.